The keep apart operator allows you to treat particles as tiny magnetic or gravitational field sources, if you'd like to think of them that way. You can control whether the force is attractive or repellent by using positive or negative force values in this parameter here. If you use a sequence of keep apart operators, you can actually produce some quite subtle simulations of interparticle forces, with large weak fields drawing particles together in the same manner as gravity, and then you can use strong small range forces to keep them apart. And in this way you can actually create simulations of gas clouds and things like that. It's actually a very interesting operator, and in some ways it actually gives you a way of treating particles as small soft collision objects, which is also quite interesting. So it's quite actually a very useful and powerful little operator. So let's have a look at the parameters that it offers. The first parameter is called force, and it controls the actual strength of the force that this operator creates. As I said earlier, you can use both positive and negative values to create positive or negative forces. And by positive I mean the operator will actually push particles away from each other, and if I use negative forces it will actually pull particles together. If this operator being called keep together, then those relationships would have been switched. But as it's a keep apart operator, positive values keep apart and negative values actually suck the particles together. So each particle gets its own little gravitational field, which is actually very cool. The next parameter is acceleration limit, and this is used to control the maximum impulse that the actual operator can give your particles to push them towards or away from each other. You shouldn't use, you should note that as the particles affect each other and change each motion, they're also affecting their orientation. So you may see some quite large shifts in the particle orientation, as can be seen in this particular example that we have here. You can deactivate this option via the associated checkbox, which you can see here. Speed limit, which also has a checkbox, is used when keep apart pushes or pulls particles using its force, and it has the ability to accelerate them to actually quite high speeds. This parameter can be used to set a level beyond which the particles will not be accelerated anymore. The need for this parameter can be reduced by using drag forces within your flow, as I've done with this particular example here. And again, you can disable this option via the checkbox, as I've just said. So, you know, if you've got a particle flow and you're using keep apart operators, the acceleration limit can actually be quite high in some circumstances, and that can actually make your particles accelerate at very high speeds. So this actual speed limit acts as a check, a maximum speed beyond which the operator won't actually accelerate your particles anymore. So it's quite useful in some circumstances when your particle motion's getting out of hand and there's too much speed, too much energy is being put into the particles basically by the keep apart operator. So the next options that we have are a toggle. You can toggle between absolute size and relative to particle size. So the way this works is you have a core radius and you have a fall off zone. So currently, if we play our current example, you can see we have our particles, and in this case they're actually pushing each other apart. And at the end of the animation we actually have a force operator, a force that actually flies through our little scene here. This is actually a gravity force, which we'll show you later by turning on this particular operator here. Now you can see that as the particles are birthed, they try to keep apart from each other, and it's using these two core values. The core radius 1 is the radius around the actual particle. If you can imagine a little sphere around the particle, within which the full force is in effect. And then we have a fall-off zone, which is again another radius, and that is using a value of 3. So in this case we have a little hard center to our particle, which is 1, and we have a fall-off zone of 3. So in effect our particles at the moment have a sort of soft feel to them. They haven't got a very hard edge to their fields, and as a result of that they will actually push away from each other rather than bouncing off each other. If we wanted to get a much harder feel to our particle, we could actually make our fall-off zone much closer to that of our core radius, and that would actually give a much more different result. You can see here. So if we put that back to 3 or 4 and we press play again, you can see there we go, our particles actually push against each other and they're all spreading out to try and reach a state where they're actually in equilibrium. You can see with a value of 4 we're not actually reaching equilibrium, so the particles are basically freaking out and sort of wobbling around. So if we use a value closer to 3, which is what we used in our original value, you can see the